Hi, my name is Dr. Matthew Michael. I'm a lecturer of mathematics here at NGIT in Newark, New Jersey, and I've been working through the PowerPoints for the 10th edition of the Boyce and DePrima textbook. Now, these lecture notes are very much based on the textbook, so I've been kind of working through them so that my students and perhaps others can understand and focus in on some of the key factors of what's going on. So I won't finish these slides, for example, because I don't like the last example as much as the first three. But all of these are based off of mathematical modeling, how to use first order equations to model some physical phenomena. So how can we translate some physical situations into um, mathematical differential equations? Well, with first order systems, we'll talk about how to do that. And that's what's going to be frequently the hardest part about this. Then the last two steps that you see here, analysis of the model and comparison with experiment or observation, that last step is going to be kind of hard, but analysis of the model, kind of thinking through and observing, and does this make sense? Does this, I mean, it kind of goes with two and three merge really well together. Does this compare well with what we've seen before? And if it does, well, great. But it's also going to be um, key to try to keep it as simple as possible. Notice the last sentence, the analysis of the model step is that we want to simplify things down as best we can. So for example, a mathematical model in physics will frequently not count friction because friction doesn't necessarily add some of the fundamental essentials to the problem. Notice the physical essentials are preserved. And so, yes, friction changes things, and heat changes things, but it isn't always necessary. So sometimes we will simplify and not include things to make our lives easier. So, the quintessential, if no other word is better for it, textbook case of mathematical modeling is what's known as the tank problem. This is going to be a tank of water with some kind of substance being mixed into it, perfectly mixed. So we're assuming that it's small enough and those fan blades that we see there are spinning fast enough that all the mixtures are, are perfectly mixed, that the concentration of this substance is perfectly spread out across this liquid. That might be a good approximation, that might not be. And that's part of the analysis step. So, for this tank that is perfectly mixed, we're going to assume that at a certain time t is equal to 0, the tank is going to have a certain amount of salt. We're going to call it Q naught, where Q is the amount of salt, 0 represents that time 0, right? So Q naught. And it's the amount of salt dissolved in a 100-gallon tank of water. Now, take a look and notice that the water is flowing into the tank at a rate of R gallons per minute. And those R gallons per minute contain 1 pound of salt for every 4 gallons, or 1/4 pound of salt per gallon. And it's leaving at a rate of R gallons per minute. But this is the liquid that is perfectly mixed. So that's going to be key. We're going to focus in on some of the early steps. We're not going to worry so much about time steps D and E. I'll pause on those slides so you can work through it yourself if you prefer. But I'm really going to focus in on A, B, and C and plugging in some results about D. So one of the key things I want you to take from this, which is why we like this particular model, is the idea that remember that the derivative is a rate of change, right? So if I'm looking to describe the rate of salt, the amount of salt being Q of T, so how does that amount of salt change over time? Well, if the derivative is a rate of change, well, how is that possibly changing? Well, some of it's coming in and some of it's going out. So the key thing you should take from this is that the derivative, the amount of salt, with respect to time is equal to the rate going into the tank minus the rate leaving the tank. So, what's going in? Well, there is water entering the tank at R gallons per minute. We don't know how big R is or how small it is. We know it's entering at R gallons per minute. But we're not interested in water. We're interested in salt, right? So how much salt is in those R gallons per minute? Well, we know that for every 4 gallons of liquid, we have 1 pound of salt. So, in other words, if I have R gallons per minute of water coming in, that means I have R over 4 pounds of salt per minute. And if we look at that rate in, it's actually modeling what I want to see what is leaving the tank, right? So notice that first parenthesis describes the concentration of the water, of the salt in the water. The second parenthesis describes how fast the water is leaving, coming in. So it's leaving at the same rate. So it's still R gallons per minute out of the tank. But the concentration, remember the perfectly mixed liquid, well, how many pounds of salt are in the tank? That's what we're looking for, that Q of T. How many gallons are in the tank? Well, we know that the water is entering and leaving the tank at the same rate. So we're going to have a constant 100 gallons of liquid in the tank at all time. So that means the concentration is going to be Q of T pounds over 100 gallons for a grand total of a rate out of RQ over 100 pounds per minute. So our initial value problem, the amount of salt changing over time, or dq dt, is equal to R over 4 minus RQ over 100, where the amount of salt begins at Q naught. And that's our mathematical model. Not perfect, but it will do the job. So move the RQ over 100 over, and notice we can use the method of integrating factors. Now, these slides are using the technique from the book with just the definition. I don't particularly like it, but sure, why not? So we solve for mu. Well, the P of t term is R over 100. So our mu function is going to be e to the RT over 100. Plugging that into the formula, where R over 4 is the forcing term, I'm going to get e to negative RT over 100 times the integral, R over 4 times e to the RT over 100 plus c. Notice that the R over 4 is a constant, so focusing in on the integral, the exponential, the integral of e to the RT over 100 is 100 divided by r. So r times 4, r divided by 4 times 100 divided by 4, r is going to be 25. So we get our final answer here. Q of t is this function. Note, we have this initial condition, so plug that into this Q of t function, and you can solve for c, because e to the 0 is equal to 1. So you get Q naught is equal to 25 plus c, or c is Q naught minus 25. I like this form better than the following example, because, note here, part C, if you remember, was what is the limiting amount? As time goes on, how much salt is in the tank? Well, all the exponential terms are the second. There's an exponential term, it's the second. The first is a constant. This exponential has a negative root. As we all know, exponentials with negative roots will converge to 0. So this term goes away. The limiting population, or the limiting amount of salt in the tank, is 25 pounds per gallon. And this makes a whole lot of sense, because remember, we were saying that the amount of salt entering the tank was 1 pound of salt for every 4 gallons. And well, there's 100 gallons in the tank. So what's 1/4 of 100? But 25. That makes sense. So we can also talk about, before we start plugging things in, we can take a look at the direction field, but we can already predict what's going to happen. If the water tank started off with a lot of salt, So if it had 50, 70, 100, 2 billion pounds of salt in the tank, well, it can't sustain that amount of salt because the water is flushing it out. Eventually, it's going to reach its limiting concentration. Note that if we started at a low point, say at 0 or 10, note that the arrows point up because we haven't reached our maximum potential of salt in the tank yet. So it will eventually approach that limiting potential of 25 pounds. So if I plug in R is equal to 3, and I say that my initial concentration, or the initial pounds of salt, is 2 times my limiting concentration, that's 50, I plug it into my equation, and I get 25 plus 25e to the negative 3 over 100t. I like keeping this fraction here in this case, because then this doesn't happen. But in either case, you can see how long it takes to get within pretty close range of that half pound of 25. So I don't like this slide perfectly, but it's okay. Um, so I think that we talked through this model, and the model makes sense. It says the model is valid because the situation is hypothetical. Yeah, no. The model is valid because it reaches into what we understand about a mixture. It makes logical sense. You can think through and go, huh, does that make sense? Why, yes, it does. And a good model will do that, and it will validate your thoughts if they're good, and it'll also give you good reasonings on why your thoughts might be wrong in other cases. Now, there are a couple of limiting things on this model, such as the flow rates being accurate. You know, you might not necessarily have a constant flow. The concentration might not be uniform. The rate might not be uniform. The flow rate going in and the flow rate leaving might be at different rates. So there's a lot of really cool math that we can help explore what's going on. But this can be used in so many different things. Notice right here, and we'll come back to this later. Now, one of my favorite examples um, of modeling use of first order differential equations is money, because I can help explain it to my students really well with student loans. But let's start with the less depressing model. Let's talk about if we have a sum of money deposited into a bank. Well, interest rate, if it's constantly being compounded, compounding is when I say, hey, look, I have a certain rate, I have a certain interest rate, like, hey, I'm going to add 0.02% my current amount and add it to my current value in my account. So I'm constantly adding a little bit and a little bit and a little bit of money based on what's currently in my account. It's an interest rate. So this means that the amount of money changes, once again, rate in minus rate out. I'm not taking any money out of my bank account. I'm just letting it sit there. So there's no rate out, so minus 0. The rate in is what's the compounding interest? That's R, my interest rate, times what I currently have, so RS. And so solving for S, I get S of t is equal to S naught, my initial investment, e to the RT, where R is my interest rate. And if you replace this S naught with a P, you get the PERT formula that you used in Algebra 2 class. This model helps explain why we use PERT in Algebra 2. We were looking at a case where money is thrown into an account and it sits there. Or you get a loan and you don't pay it off at all. Obviously, we don't actually do that. If we have a loan, we're going to try to pay it off as fast as we can so it doesn't have that interest rate constantly eating away at us. And if we have a bank account accruing money, well, there's money coming in, there's money leaving all the time. So in counting for deposits and withdrawals, well, let's say that you're constantly changing it by a rate k. So this means that if k is positive, you're constantly going to be depositing it at the same rate, or k can be negative, and that means you're constantly taking money out. So this could be, if I say the amount of money is actually a loan amount, I might owe this amount of money, so I want to pay it off. So K might be saying, hey, look, I'm taking away this amount of credit away that's negatively hurting me. So that K, even though it might be negative, it might be a positive in my situation. Depends on what's going on. But using this, I can either use separable equations or integrating factors, however you prefer. And you're going to get the following solution. S of t is equal to S naught e to the RT plus K over R e to the RT minus 1. And if I plug in values of posits where K is equal to 2,000, interest rate of 0.08, an initial investment of, wow, it looks like they have an initial investment of 0. Well, that's nice. Anyway, if that's the case, after 40 years of that IRA, where you put in $2,000 every single year, you'd have $588,313 in your IRA. Not bad. Assuming that everything else holds even. Pond pollution. Here's a different one that's kind of cool. And I like it because look at that disgusting amount of water. 100 million gallons. So these numbers are going to haunt us throughout the whole problem unless we're very, very careful. So this is like the tank problem, but as a whole pond. So this pond is going to have a tank value, a volume of 110 million gallons of fresh water. Now, the amount of water entering the pond that has toxic waste is 5 million gallons every year, and it's going to leave at the same rate. But here's the thing. Toxic waste is cyclical, depending on is the factory open, is it not? You're going to have high points and low points. So we're going to include a cyclical function, sine. So let's construct a model that makes sense of this, and then try to solve it in a way that isn't absolutely disgusting. So, well, the change of the amount of that substance, the toxic waste, is always described as the derivative is a rate in minus a rate out. Well, rate in, we have 5 million gallons of water flowing in every year. And the concentration of waste is 2 plus sine of 2t grams per gallon. So multiply that together and we get our rate in. So the concentration of waste in the pond is the amount Q of t divided by how much water is in the pond, which is 10 to the 7 gallons, or 10 million gallons. And it flows out at a rate which is also 5 times 10 to the 6 gallons per year. Oh good, we have some cancellation. But here's the problem. We still have a term with 5 times 10 to the 6th there. That's not nice. So what's really great is we can do a change of variable, or as somebody who studies mathematical modeling would say, we scale it. So what we're going to do is we're going to create a new variable. We're going to call it the scaling variable. And so Q of t is going to discuss the amount of toxic waste in millions, right? 10 to the 6 is millions. So this is sort of like saying, hey, look, you owe me 1.2 grand. You owe me 10 grand. Or the national debt is like $15 trillion or something. We do it all the time. So this Q of t is going to talk about how many millions of grams of toxic waste, whereas Q of t would be the actual exact value. There's this direct relationship between the two, but we can actually control it in a much nicer fashion once we change the variable. Notice how much nicer the equation for dq, d lowercase q dt is as compared to the uppercase q dt is. That is something I could solve. So using integrating factors, since we do not have separable equations, I get a solution, which is q of t is 20 minus 40 over 17 cosine of 2t plus 10 over 17 sine of 2t minus 300 over 17 e to the negative t over 2. And this is just done by a little bit of integration by parts. I'm going to go there and just pause there for a half second before coming back. So notice just a little bit of integration by parts. We group by integral, we notice the pattern on the left and right, and we make our lives easier and move this the 1/16 to the other side. Now, let's talk about this actual solution rather than the math. 20 is a constant. Cosine of 2t, that goes up and down, it wiggles. Sine of 2t, wiggles. E to the negative t over 2, that's a function that decays, so eventually this will not matter at all. So what ends up mattering a lot is this cosine and sine, as well as the 20. So you can really see that negative is this almost transient quality that is, over time, it becomes less and less important until it centers around the value of 20. Hey, look, 20. That's because the central line around cosine and sine, cosine is around and oscillates around 0, and so does sine. So these two oscillate around the constant that it's being added by, so just wiggling around this particular value. And so we could also solve for this, by the way, if you take a look at this. Equilibrium solution is when dq dt is equal to 0, right? So if I ignore the sine term, so this is equal to 0, because remember sine of t will oscillate around the equilibrium, so I kind of ignore this. Okay, 1/2 q is equal to 10, or q is equal to 20. Hence the equilibrium solution right at 20, because the central line of sine of 2t is 0. This is how it makes sense. Now, whereas the first model made a lot of sense because it was a tank, and yeah, 100 gallons is a big tank, but I could actually legitimately have some stirring mechanism that could do a very good job of stirring. But could you really say that a pond which has 10 million gallons of fresh water in it could honestly be mixed perfectly? Not so much. It'll diffuse at a decent rate, but it won't mix perfectly. So this model has a little bit more issues, but the scaling is fascinating. So I like doing this problem. Just be aware that this model is not perfect. No model is going to be. They're going to be fascinating. Some will be more fascinating than others. But be aware that this model isn't taking into account all these terms right here: evaporation, seepage into the ground, absorbed in the fish, plants, organisms. I also want you to, if you want to pause and take a look at these. I mean, it's an interesting model. You can take a look at what's going on. But I'm not going to go over this. It's a little bit of physics, if you like. But I'm not going to worry about it too terribly much. If you can focus and understand on the first 3 examples, you're doing just fine.